discussion at the end, the so-called Ask Me Anything. We can grill a little bit, Stefan a little bit. So, and Tobias will be moderating the Q&A session, Tobias Orten. So you can either write your questions in the chat or raise your hand, then we can unmute you, then you can ask your questions. So now let's go back to Stefan. I would say, here we go, and the floor is yours.
Yes, thank you very much, Azadeh, for the invitation. And I hope you can see my slides. I realize you are all working on the land of this planet, but primarily, of course, the Earth is an ocean planet and maybe shouldn't be called Earth, but rather ocean, because 70%, actually a bit more than 70% of the Earth's surface is covered by oceans. And that's just one reason why the oceans are incredibly important in climate change. Let me start by quoting the famous German explorer Alexander von Humboldt. I actually went to an Alexander von Humboldt secondary school in Konstanz in South Germany. There are many schools named after Alexander von Humboldt and or his brother Wilhelm von Humboldt. My kids are also on a Humboldt school in Potsdam now. And Humboldt was one of the first, if not the first person who wrote in 1843 that humans are changing the climate, quote, by cutting down forests and by releasing large amounts of steam and gas at the centers of industry. Of course, now this is common knowledge, and we know the reason for the main reason for the climate change is the increase in carbon dioxide concentration in our atmosphere. Here we see the last 10,000 years, so it's the Holocene in terms of the CO2 content of the atmosphere based on ice core data. And I think you can clearly see the stunning increase that we have caused. We have increased the amount of CO2 in the atmosphere by half. And when you look at the numbers of the years there, marked on the right, you can clearly see how this rise has also accelerated. So we're actually adding CO2 to the atmosphere faster and faster. This has consequences for the radiation balance of our planet. It causes a so-called radiative forcing by 2 watts per square meter of Earth's surface. And this is why it's getting warmer. This is actually an observational fact that the radiation balance has been disturbed by this amount by the CO2 alone. In addition, of course, there are some other greenhouse gases that also add somewhat to this problem. And if you add heat to a system, it will get warmer. That's kind of very basic law of energy conservation, which is driving the current global warming. The consequence of that is what we see here in this slide. It's so-called warming stripes. It looks like a work of art, actually quite beautiful in a way. But every strip shows the temperature of 1 year on Earth since the year 1880 on the left. We can add on the conventional way of showing data just as a curve, same data. And we can see there on the scale that we have now reached about 1.2 degrees increase compared to the first 30 years of that time series from 1880 to 1910. And we also know that this modern warming is completely human-caused. This diagram is from the last IPCC report, but the previous one, 7 years earlier, had a very similar diagram showing that the observed warming is practically within error bars entirely human-caused. Probably we have caused even a little bit more warming than is observed, because the second most important natural factor of climate change on this time scale is solar activity, and solar activity has a slight downward trend in the last 60 or 70 years. So has slightly, the faint sun has slightly counteracted the warming that we have caused or are still causing by adding greenhouse gases to the atmosphere. We are now actually warmer than any time in the Holocene, as the paleoclimate data show. That's a fruit of decades of collecting sediment cores, ice cores, etc. from all over the planet, so that we now have a good handle on the global average temperature change over the last more than 22,000 years since the height of the last ice age. And there you can see that the global temperature, it's not only the CO2 content, but also the global temperature, which is now higher than any time in the entire Holocene. So any time since we have invented agriculture as Homo sapiens and settled down and started to live in cities and so on. It also means that you have to go back to the interglacial before the last ice age, the Eemian interglacial, 120,000 years, to see the last time that we had similarly high temperatures on Earth. This also is affecting the ocean, because actually if you look at the energy that is gained by this radiation imbalance that we are causing, 93% of that energy trapped by the additional greenhouse effect is going into the oceans. That's also simply a measured fact, and this diagram shows the change in the global ocean heat content. And yeah, this is a staggering amount of heat that goes into the ocean. In a way, this is maybe even a better indicator of global warming than the surface temperature of the Earth that I showed you earlier in the warming stripes, because this is really basically equivalent to the amount of heat that the Earth has gathered, and it is less noisy. So there is less year-to-year variability in this measure, because the oceans are really integrating up all that heat. Just as an aside, why is 93% of the heat going into the ocean? That's not because the ocean are getting hotter than the atmosphere, quite the contrary. The oceans are warming more slowly than the atmosphere, but they have a much larger heat capacity. Primarily, this is a top 100 meters or so, the so-called mixed layer, which is accessible as heat capacity on this time scale. For the heat to penetrate deeper into the ocean, that takes much longer. So the deep ocean is warming very, very slowly because of that slow heat penetration. The ocean, of course, is on average around about 4,000 meters deep, but in directly mixed and in direct contact with the atmosphere is just the top 100 meters or so. But that heat capacity is already much, much larger than that of the atmosphere, and that's why most of the heat trapped by the added greenhouse gases is going into warming the oceans. The rest, the remaining 7%, are shared between warming of the land surface, warming of the atmosphere, and the amount of energy spent in melting ice. That much to the energy budget. One result I already mentioned, melting ice, is that we are losing ice at the ocean surface as well as continental ice, but I'm not talking about the continental ice today because we're talking about the oceans. This picture shows the sea ice cover on the North Polar Ocean as it used to be until the 1970s or 80s. And this is what it typically looks like now. These are both summer pictures. And so just to go back and forth again, we have lost almost half the ice cover on the Arctic Ocean already. And because the ice is also lost about half of its thickness, that remaining ice, that means in terms of the ice volume on the Arctic Ocean, there's only about 1/4 of that ice left now, compared to what it was just a few decades ago. And we will all live to see this situation. We can't exactly tell when this will happen, but it's only a couple of decades or so away that for the first time we will have a summer which is virtually ice-free in the Arctic Ocean. If you want to look at a time series, again, we can look at proxy data from sediments to reconstruct the ice cover going back about 1,400 years or so. And you see it was relatively steady until in the mid-20th century, this steep decline began. You can see where the proxy data, the light blue curve, overlap with the modern observations that started around 1850. And then those again overlap with a satellite trend that the modern satellites show, where we have every year, every day, basically, we have updates of the sea ice cover, the sea ice extent on the Arctic Ocean. And so it's basically in free fall and will hit zero very soon. There was a recent, couple of years ago, historic Arctic Ocean North Pole expedition by the German research vessel Polarstern, led by my Potsdam colleague Markus Rex, who they crossed the Arctic Ocean up to the North Pole throughout a winter and then summer. And Markus, when they returned, basically said to the media, "We watched the ice dying." So that much about sea ice. I now want to talk about another aspect, that is sea level. Of course, the melting sea ice practically contributes nothing to sea level rise. So don't draw this connection here, because the sea ice is already floating on the ocean. And so when this melts, it's just like melting an ice cube in your whiskey. It actually doesn't add to the level. But the sea level rise, I will show that in a minute, is due to thermal expansion, because water expands when it gets warmer, and to the melting of continental ice, like the mountain glaciers and the big ice sheets in Greenland and Antarctica. You can see that the sea level has increased worldwide by about 20 centimeters so far. And you can also see that this increase is accelerating, which is not surprising, because it's exactly what we expect. The warmer it gets, the faster ice melts. It's just very elementary physics. And so the warmer it gets, the faster the sea level will rise. And I still remember the day when I saw the first talk with the very first results of the first few years of satellite data of global sea level. And those satellite data immediately showed a strong increase in the global sea level. Until then, we only had the tide gauge data that are also shown here in blue. And these tide gauge data, of course, collect sea level data only along coasts. We did have no information about what's going on in the interior away from coasts. And so it was quite a revelation to see the first satellite data of sea level and to see that they actually match what we had already seen on the tide gauge data. And by now, even in this relatively short satellite series, we can see the acceleration just by eye. The satellite series starts in 1993. The sea level doesn't increase by the same amount everywhere. You can see this map here, which shows the trend from the beginning of those satellite data, 1993, as I mentioned, up to early this year, this spring. They're always online, actually. The NOAA website, satellite altimetry, you can look that up. You can always find the latest data there. And you can see some interesting differences. In some areas, like the boundary currents here, the Kuroshio of Japan, you can see that there are ocean eddies, these small-scale structures that sometimes move and shift, so they are changing. So this eddy activity you can see. You can see some areas with larger sea level rise, like here the warm pool in the tropics, which is also the area where the sea surface temperature is the highest, and that there it has obviously collected more heat and increased even more. You can interestingly see a minimum of sea level rise here south of Iceland. I will talk about this patch later on in my talk, because this is the only ocean area on the planet that has actually cooled in the last 100 years. And you can see a thing here that around the coast of Greenland, sea level has risen less. That is probably an effect of the gravity effect, because if you only look at the effect of melting Greenland ice, for example, on sea level, the melting of the Greenland ice sheet alone by itself will lower the sea level on the Greenland coast. That is maybe to lay people counterintuitive, but it is simply due to the fact that the big ice mass on Greenland has a gravity effect, and it attracts the seawaters from around. So this gravitational attraction leads to raise the sea level on the Greenland coast. And if the ice sheet melts, the gravity effect gets less, and the water moves away from the Greenland coast. And so that's why melting ice sheets actually lead to sea level rise away from the ice sheets everywhere else, but not right where the ice, in the vicinity of the ice sheet. This just as a little technical detail. So to reconstruct sea level on longer time scales, we can again turn to sediments, in this case coastal sediments in these coastal wetland areas, where the sea level kind of where the gosh, I just can't think at the moment of the English term. I think it's called a moor in British anyway. The sediments there.
You mean peatland, Stefan? Peatland?
Yeah, exactly. I was looking for
Okay.
that for that word. Exactly. So these get flooded every now and then, also by the tides, and so the sediments accumulate there, and they grow with the sea level. So when the sea level rises, more and more sediments accumulate, so that these coastal marshes, they keep up with a certain amount of sea level rise if it's not getting too fast. And you can drill into them and get a whole sea level history going back thousands of years. And yeah, here you can see me in North Carolina on the Outer Banks, joining some American colleagues for the field work there, collecting these cores. And we published a study which actually is a compilation of many such cores taken around the world to get a global average picture of the sea level changes by century since the birth of Christ. And you can see that there has been no century where sea level has increased as fast as in the 20th by far. Sorry that this is in inches, because it's from an American website, Climate Central, which just produces nice graphics for educational purposes. The graph is nicer than the one we have in our paper, but it is in inches, whereas in the scientific paper it's in centimeters. But again, I already said that it's about 20 centimeters in the 20th century. And this is unique, not surprising, because the warming is unique, of course, as I showed earlier. And therefore, the logical consequences also that we see an unprecedented rise in sea level in the 20th century compared to the centuries before. And I remember many discussions with so-called climate skeptics on the internet, etc., which have claimed, oh, well, sea level is rising since the last ice age. You know, it has nothing to do with human-caused global warming. One simple piece of evidence, for example, is the Roman fish ponds, I took this picture during an excursion in Italy on the coast near Rome, where you can see fish ponds that the Romans built at the time, and they have little gaps where they are connected to the sea, so that at high tide, fresh ocean water would flow into these fish ponds. And that's why they are built exactly where the sea level was at the time, 2,000 years ago. And think about it, you know, if the sea level had been rising by 20 centimeters per century all along since the last ice age, then these Roman fish ponds 2,000 years ago, they would by now be flooded by 4 meters of sea level rise, and they're obviously not. So this just demonstrates that is one little piece of evidence before we had all these sediment data, which already clearly showed that it's not normal that sea level rises by this amount. It's a modern phenomenon as a direct physical consequence of modern global warming. So let's look at the detailed sea level budget since we have the satellite data of that rise since then. About 42% is due to the ocean thermal expansion and 44% is due to ice melt. So you can kind of say roughly half thermal expansion, half ice melt, continental ice melt. You can distinguish in the continental ice melt the mountain glaciers, 21%. The European Alps have lost more than half of their ice mass already in the last decades. And then the big ice sheets are responding more slowly to the warming, but they have much more ice to raise sea level in the long run. I'll get to that. And so about 15% of sea level rise is coming from Greenland and 8% from Antarctica, but they are going to be the biggies in the long run. Now what's missing to 100% there has to do to some extent with the uncertainty, because within uncertainty, the separate determinations of these individual factors add up to the observed sea level rise, but not to the last couple of centimeters. And there are other factors like water pumped from the ground for irrigation purposes, which also raises sea level, because it means there's less water stored underground on land then, and more ending up in the oceans, because when you irrigate your field, the water will evaporate or perhaps run off into the sea. And in any case, that is also a relevant contribution to sea level rise. Now, if we look into the future, the amount of sea level rise obviously depends on our future emissions and the future global warming. And the latest IPCC report projects by the year 2100 somewhere between 0.5 meter and 1 meter of sea level rise, where the lowest scenario, this blue one, that is kind of a Paris Agreement compatible scenario where we stop global warming close to 1.5 degrees. Warming will then in this scenario be stopped around the year 2050, but you can already see that the sea level doesn't care about that very much. It continues rising. All we achieve by stopping global warming is that we will prevent a further acceleration of sea level rise. Because the sea level responds extremely slowly with a lot of inertia. It takes thousands of years for the ice sheets to come to a new equilibrium with a warmer climate. And so they will just keep melting for thousands of years after temperature is stabilized. And so we cannot prevent a lot of sea level rise in the future anymore. It's too late for that. We can only prevent it from coming faster and faster, as you can see here. Another important aspect is that there is a big uncertainty, one-sided towards the high end. So it's a good example for why uncertainty is not our friend in global warming. There's a one-sided uncertainty that it could be much worse. The IPCC has written in the last report that they cannot even rule out more than 2 meters of rise by the year 2100, which would be totally catastrophic for most coastal areas. Even 1 meter is very catastrophic. And the IPCC further says by 2150, they can't rule out 5 meters of global sea level rise. And they also published an estimate for the year 2300, when you let these ice sheets melt on for a while. And then even for the Paris scenario, the blue one, it could be 2 meters, 3 meters, and with high emissions, it could be up to 7 meters. Or look at the arrow up the top, it says sea level rise greater than 15 meters cannot be ruled out with high emissions by the year 2300. So we are really causing a very big legacy for many generations to come in the future, because the sea level will not just be higher at a stable level where you can adapt and build your city at the new coastline. It will be rising at an unprecedented speed. So basically you can't build any lasting structures anywhere near the coastline in the future centuries anymore. Here's a very long time scale, a look at 10,000 years into the future. It starts from the past. You see again 20,000 years ago the height of the last ice age, and you see the sea level rise into the Holocene. That is a rise of 120 meters worldwide from the melting glacial ice masses. At the time this transition from the ice age into the Holocene, 2/3 of the glacial ice masses melted. We have 1/3 left today. That's more than 60 meters worth of sea level rise potential we have in the form of ice on Antarctica mostly, and on Greenland. And so depending on our emissions in these future scenarios that you see here on the right, the lowest one is a Paris-compatible, like 2-degree warming scenario. It will get us to 25 meters sea level rise in the next 10,000 years because of parts of the ice sheets in Greenland and Antarctica will be melting by then. And of course, 10,000 years is a long way off. You probably don't care about this, but if you look at the rate of rise at the bottom curve here, you can see that the fastest rates are actually in the next few centuries. That's kind of the worst problem that is going to be caused there. Actually, here on these maps show how much ice is left on Greenland and Antarctica in the worst case scenario here, the top one. Greenland completely ice-free, and only a small part of Antarctica, maybe 1/3 or so ice covered, whereas today the entirety of Antarctica is ice covered. I already mentioned that there's enough ice to raise global sea level by 65 meters, and this would go on the Statue of Liberty in New York. It would go up to her waist like this. This is a huge statue for those who have not seen it so far. And this made the National Geographic cover in 2013. Still, many people don't know this. So now I somehow lost my ability to forward the slides. Don't know why. Okay, there we go. Maybe it was just slow responding. So you can imagine what just even a 1/2 meter of rise means for a place like this. This is the capital of the Maldives, Male. Yeah, there's nothing they can do basically if a big storm surge comes and the sea level is a little bit higher. And so what they are doing is they are building a new island that is 2 meters higher, where they plan to resettle much of the population. This is only possible in very special cases when you have a lot of very shallow ocean nearby with a lot of sand at the bottom that you can just pile up to create a new island. The latest IPCC report concluded that coastal flood damage is projected to increase at least 10-fold by the end of the 21st century and represents an existential threat for coastal communities. Now, there's not only these physical changes, but carbon cycle also. The ocean takes up 24% of the global, our global CO2 emissions. About half of them stay in the atmosphere, the so-called airborne fraction, and about a quarter ends up on land in terms of forest growth, etc., absorbed by the trees and vegetation, and 24% ends up in the ocean. On one hand, that's good because otherwise the rise in the atmosphere would be even faster and we'd be in even deeper trouble by now. On the other hand, it causes ocean acidification because CO2 dissolved in seawater forms carbonic acid and increases the acidity of the ocean. That threatens a lot of marine life, all these calcifying organisms like these microscopic plankton shells that you see here. On the left-hand picture, this is what it should look like, a healthy one, and on the right-hand side, one that is corroded by acidic seawater. And if we don't stop emitting CO2 pretty soon, then already in the second half of this century, parts of the oceans will be so acidic that the ordinary seashells that you find on the beach will be dissolving in the seawater. So this ocean acidification problem in itself alone would be enough to stop emitting CO2 because these critters are the basis of the marine food webs. So even if CO2 didn't cause any climate change, that would be enough reason to stop using fossil fuels. Another effect that affects a lot of people on land is that warmer oceans enhance the power of tropical cyclones because tropical storms draw their energy from the heat stored in the upper ocean. And if we just look at the satellite analysis of what are the strongest tropical storms since the satellite observations began in 1979, in these 8 different tropical cyclone affected regions, then you will find that in 7 of those 8, it's been really very recently. Just by random chance, the probability of this would be close to 0. And by now, actually, it's not only the very strong storms that have been reanalyzed from all those satellite images collected for decades, but all storms. And there is a very clear trend to increasing stronger storms. So we don't expect to get, and we do not see more tropical cyclones, but we see stronger tropical cyclones, which is logical because we're not interfering with the kind of genesis of these cyclones, which just come from thunderstorms and stuff like that go over the oceans. But we are increasing the potential for them to get very strong by providing a bigger energy source for these storms. And the share of major hurricanes that are reaching category 3, 4, and 5 has gone up from just over 30% to now nearly 40% in those 35 years studied there in this paper. And so that's another prediction of climate science come true. Tropical storms are getting stronger. Now I want to talk a bit about one of my main research topics, the Atlantic overturning circulation. Part of that is the Gulf Stream, and in public it's often discussed as a kind of Gulf Stream, but the technical term is really Atlantic overturning circulation or Atlantic meridional overturning circulation and or thermohaline circulation. And this is a system that has critical thresholds, as I will show in a minute. And there was a very nice article in the New York Times about 1.5 years ago on this, pointing at the dramatic dangers involved in this system. And here's a simplified picture of the circulation, which basically consists of warm surface water flowing north into the high latitude northern Atlantic, then giving off heat to the atmosphere, thereby getting denser and heavier, and the water sinks down to about between 2 and 3 kilometers depth and returns at this depth to the south. And so it works like a central heating system. The warm water is flowing north, cold water is flowing back to the south, and a lot of heat is given off to the atmosphere in that region south of Greenland and Iceland. And if you look at old IPCC reports here from 2007 with the predictions for the future, then you can already see that in a strong warming scenario, the entire globe warms a lot, the land warms more than the ocean, the Arctic warms even more. All these things are very well known. But you see a clear minimum of warming where there's very little south of Iceland and Greenland there in the northern Atlantic. And so this has been predicted by climate models for decades. And the reason is a weakening of this Atlantic overturning circulation. And if you look at the observed data, this is from the European Atlas of the Seas, the trend since 1993 basically, they show actually a cooling in this region, whereas the rest of the ocean has warmed. And the same is true for the trend for the last 100 years. This region there that is blue in this nice diagram is the only part of the world ocean that has cooled in the last 100 years, whereas all the rest has warmed. Now, why is this? Here is a simulation of a climate model, a very high resolution climate model with especially high resolution ocean, which has the best ocean circulation of any climate model I know. And it shows in this case, a paper that my PhD student, Lev Cesar, published together with me and a few other co-authors. It shows the modeled temperature, ocean surface temperature change in response to a CO2 increase relative to the global mean temperature increase. So anything that is blue has either cooled or warmed less than the average, and anything that is orange has warmed more than the average. And that is the model prediction for the response to CO2 increase. And in the model, we know everything, basically. We have all the information, and we know why this funny pattern here exists. This cold patch is due to a weakening of the Atlantic overturning circulation, so less heat transport reaching this area here. But this warmth on the American coast is also due to a weakening of the Atlantic overturning circulation, which then actually means that the Gulf Stream shifts closer into shore for reasons that basically physical oceanography students have to understand. You don't have to understand it. It has to do with vorticity conservation on a rotating sphere where the deep North Atlantic deep water crosses under the Gulf Stream. So you have to preserve the vorticity, that's the angular momentum in the water column there. And so when the deep flow gets weaker, the Gulf Stream moves closer inshore, causing this excessive warming along the American coast. And this is the observational trend since the year 1900 in sea surface temperature. And you can clearly see that cold blob here south of Greenland. This is now, as I mentioned earlier, this is a more than 100-year trend. But you can also see this exceptional warming on the American coast. We don't have the resolution to see this blue part, which is part of that shifting of the Gulf Stream northward, because ocean observations basically, how fuzzy the picture is. We don't have constant everywhere ocean observations for more than 100 years. This is shipborne observations, and so it's all heavily smoothed. But you will agree that we have this fingerprint pattern of the Atlantic overturning slowing here in the observational data. And when we scale this with the help of model simulations, this corresponds to a 15% weakening of the Atlantic overturning. There is also proxy data for changes in this Atlantic overturning. We published that the year before last, actually. And you see reconstructions here that show the last 1,500 years of Atlantic overturning based on various different sediment data. These are the locations of all these data sets and different proxy measures, including this curve, for example, is grain size at the ocean bottom, which tells you how fast the current is that flows along the bottom. And you see this pretty stable situation and then a decline here. Last week I was at the International Conference on Paleoceanography, where actually David Tornelli, who did this work, presented on his poster results showing that the Atlantic overturning, according to these proxy data, now at the end here is the weakest, not just in more than 1,000 years, but actually more than 10,000 years. So in the 20th century, we see this general decline in all these curves of the Atlantic overturning. And one reason is this addition of meltwater from Greenland, including increasing rainfall in those latitudes that dilutes the ocean waters, makes them less salty, and prevents the sinking down of the surface waters in this region, which drives the Atlantic overturning circulation. This has consequences already today for our weather. There's a nice study by Aurélie Duchesse and colleagues from 2016 where they showed that if there's a cold blob out in the ocean down here, this creates air pressure anomaly in the atmosphere, which basically is a low pressure centered over the cold blob, which makes the jet stream and the general airflow go around the southern side, and then Europe gets its air from the southwest. And this is exactly the kind of situation that creates these excessive heat waves in Europe, as we have seen last summer. This is a little bit different, by the way, from the Day After Tomorrow movie, but this is because, let's just quickly go back, this is because we're talking just about a 15% weakening with a cold blob out here. If that scenario in the Day After Tomorrow happens where the circulation breaks down altogether, this cold patch will expand over land and will really make Europe very cold. But with this moderate weakening, that's not the case yet. And I mentioned it, the Atlantic Ocean has a bifurcation, a tipping point. This has been well known. I published a review article on this in Nature 2002. And the behavior is if you add more fresh water on the x-axis here, go to the right, like meltwater from Greenland, you move the circulation on this stability curve to the right, and eventually you hit this tipping point where this curve bends back on itself due to a positive salt transport feedback, and then you fall off the cliff here and the circulation breaks down. So I want to come to a close with a last very short point, coming again to the marine biology. Also, coral reefs, corals have a tipping point. They have a tolerance limit for high sea surface temperatures. Beyond that, the corals bleach because their zooxanthellae leave them. These are symbionts that make the corals so colorful. And so they turn white when it gets too hot. Here you see the Great Barrier Reef coral bleaching in 2016 marine heat wave, and then a few months later it's overgrown by algae, by seaweed, and the coral reef will not recover. And yeah, 2016 was the first big coral bleaching event on the Great Barrier Reef affecting the northern half. 2017 the middle portion. 2020 the southern part, the cooler part, was affected, but in each time the bleaching area corresponded to where the warmest sea surface temperatures occurred. So it's clearly temperature driven phenomenon, not yet driven by the ocean acidification. And it's worldwide. This is just 2015 and 2016. Only the blue reefs out of those 100 that have been observed escaped that coral bleaching. So the IPCC warned that for 2-degree warming, practically all coral reefs will be lost. If we succeed limiting the warming to 1.5 degrees, between 10 and 30% could be saved. That is very depressing finding, actually. So I'm coming to my conclusions. Global warming is unequivocal. We're in the middle of it. I don't think I have to tell you that. And the impacts are not subtle. They are felt around the world now already. Millions of people suffer from extreme events. As we speak, 1/3 of Pakistan is underwater and so on. But also the physics, biology, and chemistry of the oceans are being changed in a major and detrimental way by it. And so we must cut the global greenhouse gas emissions in half by 2030 to still keep the 1.5 degree Paris limit. as the IPCC report, the latest one, has concluded. So that's in 8 years. That is a very stiff order. Every year counts. With that, I thank you very much for listening. I have written one book about the climate crisis together with my colleague David Archer from Chicago University, and with a marine biologist, Catherine Richardson. We have published a book, Our Threatened Oceans, which kind of covers what I have told you today, but a lot more about marine biology. I'm just the physicist here, so I only touched upon the biological part. So thank you very much, and I'm ready for being grilled by you guys. Thanks for listening.
Yeah, cool. Yeah, thank you very much, Stefan, for the very interesting presentation. Guys, you can follow Stefan also on Twitter. I saw that most of your tweets are in German, but I think you have also some tweets on English. So maybe
Well,
for
it's roughly
non-speaking.
half and half. It depends a little bit. Sometimes when there's a lot going on in Germany, yeah, political debates, I tend to post more German stuff. But in Twitter, you can select to see only English language tweets if you don't want to see the German ones.
Yeah, I mean, I think if you can say that you are, what kind of account do you have? I mean, what is how they can find you on Twitter? Is it like at Stefan Rahmstorf, or
no,
how
it's
is
just
it?
at Rahmstorf. It's at Rahmstorf, and all you need to do is spell my surname right.
Okay, yeah, okay, very good. So I give the floor to Tobias for the further questions and Q&A.
Yeah, thank you very much, Azadeh. Thank you very much, Stefan, for this very interesting talk. I learned a lot. I studied physics myself, but because it was so much in detailed, I also didn't get 100% of even the physics you explained to us. So I would like to move the focus of the question and answer session a bit more from the physics and from the scientific focus to the public debate that is happening on climate change, and especially on climate action to protect the climate, because everything you have shown is on the one hand very, very fascinating. I always feel like I'm in a movie when I see these presentations. I'm amazed by how much we understand, but at the same time I think we are a bit shocked standing in front of in front of a snake, shocked, do not know what to do, and simply see things happening, right? So, and this is what everyone here wants to change. You want to see action so that, for example, sea level rise is not as bad for coastal and the environmental systems altogether. And we also invited you because we know that you are very active, engaging in the public debate in Germany and in Europe, probably also with your colleagues all over the world. And we hope to learn lessons from you, how to effectively communicate climate change. And I would open the floor to everyone participating, asking their questions. You can raise your hand. In the top right corner of this meeting, you have different symbols you can click. There's the reactions oder Reaktionen button. There's so eine Hand, there's a hand and a smiley. You can click and raise your hand. We can unmute you and then you can ask your question, or you simply post in the chat your question, and we will either in German or in English, we will ask them to Stefan to answer it. And here there's the first question by Nora, and I hope you can now actively ask the question because I granted you the microphone.
Thank you very much. Can you hear me? You can't see me, right? Okay.
Yes.
Great. Thank you, Stefan, for this great summary and insights, and thank you, Azadeh and Tobias, to host this. I have so many questions, but one of the really practical questions might be, do you see any real chances to, if not turn it around, but really utilize maybe some modern techniques? Or sometimes we see startups and we kind of gather hope again that somehow they clean the oceans, help the oceans, and do some counteracting. but maybe this is just to ease our souls, and you can tell us that this is not going to happen. Maybe you can say something about this. How are the hopes, apart from what we all have to do to save the climate, obviously, to have some impact from modern technologies or innovative ideas? Is there hope?
Well, I mean, I think there's no way around going to zero emissions as fast as possible. That is absolutely the key, also for saving the oceans. Of course, maybe you're referring to technologies to remove CO2 from the atmosphere, which are being tested. There's one test plant on Iceland right now, but it's really a drop in the ocean in terms of the volume, and the costs are really, really high, much higher than replacing fossil fuels with renewables. So basically, number one is we have to cut our emissions. There may be some technological fixes for a small amount of remaining emissions that we can't easily get rid of, maybe from agriculture, but there is no hope for a techno fix. I don't know, maybe you're referring to plastic pollution, where there have been some startups trying to collect plastic from the ocean. And of course, that has nothing directly to do with climate change. It's a different problem, a pollution problem. But also here, it's pointless to go out with ships and try and collect a little bit of plastic whilst I don't know how many tons of it every minute go into the ocean. You really have to plug the sources first, which if you look at where the plastic comes from, it's mainly rivers in Asia, which many countries don't have really good rubbish collection systems, so that nothing is left to be kind of blown away by the wind and washed in the oceans.
Okay, thank you very much, yes. Stefan. Yeah. And there's a question in the chat by Kevin, and he asks, what is the potential contribution of mangroves as a net sink of CO2 emissions in marine ecosystems? And how can this be linked to acidification in the oceans?
Okay, well, this is a difficult question, which basically I can't answer. I think mangroves will store CO2 just like forests on land, as far as I can tell, but I don't really know anything much about mangroves. And the problem, I think, at the moment is not that we have mangroves as a solution because they are being grown, but rather they are being destroyed, as far as I can tell. And so this just adds to the problem. So it's like on land, the preservation of the existing mangroves is the key. Just like on land, we should preserve the natural forests, which is number one before you think about planting new forests, because of the natural forests always have much more biodiversity and a much greater value compared to anything that we can plant.
Okay, thank you very much. I don't see other questions by now. Probably people are still thinking, but I have a question myself, and especially from the perspective of young people who still can decide on what to study and where to engage in their professional lives, but probably also from the perspective of people who already have been working a lot because they have limited time to still act on the problem. What do you think is the highest leverage to engage? And you said shifting from fossil fuels to renewable is key, sure, but there are different angles to approach that, right? You can be a technician, you can be a politician, you can be an activist. What do you think is the highest leverage for people now engaging, even on the longer perspective, if they plan for the next 10, 15 years?
Well, first of all, I would say working on the solutions rather than studying the problem like I have been doing in my career is, of course, now called for. I don't think we need a lot of people to enter basic climate science or so, because most of it is understood, basically. So, and much more pressing is to actually solve the problem. Now, where you best do this, I think, depends a lot on where your particular skills and talents are. You should always look at yourself and see what are my skills, and then contribute those in the right place. So if you're like a technically minded person, then yeah, sure, become a technician. If you're more kind of a political animal, you may want to enter politics or join an NGO. And there is actually a lot of jobs opening up in companies, in NGOs, in governments, for people who understand climate change. And so I think on all different levels, there's a lot of new opportunities arising. Nature actually had recently a feature on this, giving some examples of people that work outside academia on climate issues. And yeah, I think I personally have friends who have done that. You know, some people from young colleagues work for a financial investment company who are looking at green investments. Other colleagues I have founded climate analytics, who are basically doing a consultancy and analyzing climate policies, etc. There is different opportunities there depending on your skills and basically what you enjoy doing, because that is where you are going to be best.
Okay, thank you very much. And this is in a sense a good answer also for myself, and I think our activities at betterSoil, because we try to especially do something because we are convinced that we have the solutions already. But always when you come from a scientific perspective, you feel you don't know everything to act. And that's probably the problem that people need to overcome, to live with the uncertain, because you're sure you know enough. There's a
Nobody
question.
knows everything.
It's always suggested that people like you or others know much more, and you should achieve that. We have another question by Birgit in the chat, which I will read out. And then there's a question by Vincent, and Rüdiger also posted something in the chat. So Birgit herself claims to be a big fan of preserving cultural assets, so we shouldn't misunderstand her question. And the question is that engineers are working on an audacious project for Venice to pump seawater into the city's subsoil and raise it by 25 centimeters. I perceive a dilemma between putting money, effort, and research into saving threatened cities versus curbing the drivers of the climate crisis. How do we find a good balance here between probably preserving what is valuable to us and probably deciding what not to serve the greater good by investing money at a different place?
Yeah, well, that is, in a way, is a good question. It is kind of, if you look at it in a broader sense, it's a question of adaptation versus mitigation, right? You can see this scheme for Venice as a kind of an adaptation to sea level rise. Venice cannot be saved by mitigation, that's for sure, because of that sea level rise continuing for centuries on, as I mentioned. But you know, I think obviously we have to do a mix of both. We have to adapt to climate change and we have to mitigate it. So this very unsatisfactory answer, I know, but I don't know how there could be a good answer to this. I can't give you percentage of money you should invest in mitigation versus adaptation or so. I might add on Venice, actually, I didn't know about this scheme to raise the kind of expand the subsoil, but I have been to a couple of workshops in Venice discussing whether Venice could be saved by these Moser floodgates that have been built that I don't even know they were supposed to go into operation anytime now. I don't even know whether they are in operation already, but already this is quite a while ago. It's like almost 15, 20 years ago, I think, that we had this the first workshop on this, and already people were pointing out that these floodgates for Venice did not nearly account for enough sea level rise, and it wouldn't take long for them to become pretty useless. especially since if you close the floodgates, the rivers will keep dumping water into the lagoon, and the sea level rise will go around it and come then from inland, etc. You're not going to save Venice by these floodgates. So I'm not surprised that they're now thinking about other means. But this is just a little political comment. There was this workshop and subsequent, the year later, a big conference hosted by the Venice UNESCO office. And because in this workshop, there were several scientists, including me, that cast big doubt on the Mose Floodgate project, which had been supported by Berlusconi and his mates, a network kind of thing, with a lot of money invested. That obviously some very powerful people didn't like the fact that there would be an international conference on this. And about a week before the conference was starting, when we already had the air tickets and the hotels, the conference was cancelled. And the head of the Venice UNESCO office was sacked. And apparently this was through Berlusconi and his influence into the Paris headquarters of UNESCO. So it was a clear case of political corruption. Don't quote me on this. I don't want to be sued by anyone, although it's maybe too long ago for this to happen. But I was quite shocked how things happen. You know, how you can just, somebody dislikes that people hold a scientific conference and just forces it to not go ahead and sack the person who organized it. It's shocking.
I mean, that's not the first case of unliked voices being silenced in a sense. So you're probably in line with people like Galileo, even though consequences were not that harsh today.
Well, that is a rather flattering comparison. Compare me to Galileo, but yeah, I know what you meant.
Okay, good. Don't get me wrong on this. We have Vincent in the line, and I activate camera as well because I see I'm able to do this.
Yeah, thank you very much, Professor Rahmstorf and the whole betterSoil family for organizing this wonderful presentation. My question will be a bit related to what Birgit already asked. Is there a way we can turn this current doomsday scenario around to our advantage? For instance, you're saying the ocean has so much potential, storage potential. Is there a way we can harness this potential from the ocean and of course plus other places for the sake of saving humanity, maybe produce power and transmit it to places where there's no power, or use that water for, like in the case of Venice, where they want to lift the city up, or maybe channel it somewhere like agriculture, or desalinate it and use it for agriculture, because as you said, sea levels are rising, ocean levels are rising, and there's no one who live this one alive. We are all here to stay. We are all here to live, and I think we should be able to adapt and find innovative ways to overcome these challenges. So, what do you think? Is there a way we can harness these calamities and challenges, turn them around to our advantage, and make the world a better place? Thank you.
Yeah, well, there is one thing that has been discussed with the ocean, that is CO2 storage. First of all, in the ocean waters, there have been schemes proposed like that, but that of course would actively contribute to ocean acidification, so it's a kind of a non-starter. There have been schemes actually with studies, field studies being done by another German institute on ocean fertilization, so that in areas where the marine productivity is iron limited, you dump iron into the ocean. It's just a trace element that the algae need, that they're missing there, and you can create an algal bloom. But it turned out that actually there was very little so-called export production. That means biomass carbon that was going into the deep ocean. And if it just stays in the surface mixed layer, it doesn't help. So that was a kind of a non-starter and has also negative side effects. Yeah, we could discuss the storage of CO2 in the sea floor in old gas fields. That may be a bit more viable, but also not in those huge amounts that you would need. I think that kind of the idea of carbon capture and then storing it under the seafloor is also by sheer costs, by leakage problems, etc., pretty well a non-starter. What you mentioned to generate energy from the ocean, renewable energy, is a more viable idea. There are tidal power stations already in France, for example. Not many locations are suited for that because you have to have some embayment with a very high tidal range, but there is a few locations like that on Earth that could be used. And maybe the most promising is wind power and maybe wave power. In Scotland, there's a wave power plant already. If you have big waves near the and steady waves near the shore, you can harness the wave power. But the most viable, which is already used in a big way in the North Sea, in the Baltic, etc., is offshore wind, because the wind blows much more steadily over the ocean than on land. And the trend, I think, for the future is to go to floating platforms that don't have to be in shallow ocean waters anchored at the bottom, but that they can float on the ocean. And so on steep coastlines like off Japan, for example, you could harness wind power, offshore wind power in this way. Denmark is to a large extent already powered by offshore wind.
Thank you very much. Then we have a question in the chat by Rüdiger, and he says, "Thank you, Stefan. Very insightful presentation, yet depressing. You mentioned one article of yours showing the consequences that was already published in 2002, so 20 years ago. How come you were not heard back then? Any insights from your side? What has changed since then? And are you frustrated by not being heard?"
Well, I mean, I would generalize this to science in general not being heard. I can very clearly remember 1992. This was the Rio Earth Summit. And when I saw on the news the Rio Earth Summit has passed the United Nations Framework Convention on Climate Change with the goal to prevent a dangerous global warming, I was thinking, finally, you know, after all these years of debate, finally the world has woken up and is passing a global climate treaty. We all know that since 1992, the emissions have kept increasing rather than being brought gradually down to zero. This is really depressing, and I think the main reason is the power, the lobby power of the fossil fuel industry, which has mounted a campaign with hundreds of millions of dollars, actually probably more than $1 billion, a disinformation campaign triggering this false climate skeptics debate in areas where there has long been a scientific consensus. And yeah, it is depressing. I'm more optimistic now, especially because of Fridays for Future, with their global protest movement, have put a lot of pressure on politicians, and also the extreme events are taking on an intensity that the public is gradually waking up and is voting out governments that are in the hands of fossil fuel companies like the one in Australia recently.
Okay, thank you very much. And we have one last question by Lisa, because you said you were about to leave at 15 past 5. And the question is, I would be interested in your opinion, Stefan. Do you find talking about these disturbing scenarios with people around you helps winning more people to fight climate change, or do you avoid talking about it? And maybe I would add up on what is the best question, the best way to approach people in order to motivate them to engage and fight climate change.
Yeah, there is actually now a lot of literature on this. I recommend, for example, Catherine Hayhoe's Twitter feed, and she has nice videos. She's very good, maybe top of the world in how to win people over. You basically have to kind of first find a common value ground, common interests with people. If you approach them like a missionary or induce guilt feelings or feelings of helplessness, that is not very good. I think it's most important is if you talk about solutions, and it can help to tell people about things you're doing. Like I have installed a heat pump in my house, and so just talking to people, saying, "Hey, I've installed a heat pump." I mean, at the moment, that's you run in open doors with this, with the horribly increasing gas prices in Germany. Everyone wishes they had installed a heat pump a year ago or so. I was lucky to do that in time. And I mean, the neighbors see when you put solar panels on your roof, and I have spent my life cycling to work. So it helps if you sometimes talk about how you enjoy biking through town rather than being stuck in a car in a traffic jam and traffic lights, etc. Just talk about positive lifestyle changes that you have made. And maybe don't brag about flying to the Maldives every year or so. This is maybe putting forth a bad example. And yeah, I think try to be non-confrontational. Otherwise, people just harden and they lock into their own belief system. And they become defensive.
Thank you very much. Thank you very much, Stefan. Thank you very much for interesting questions from the audience. Thank you very much that you all joined. We were very delighted that you accepted to give a talk here at the betterSoil Academy, so to say. Our expert talks are part of the betterSoil Academy, and we will continue doing this and hope to see you soon on our next webinars. You can, of course, also contribute to our crowdfunding campaign at Better Place. Look in social media, look at our website. You can find all information and the information that we will post in the months to come. And I would give the word to Azadeh, say thank you for a closing remark.
Well, I first also want to thank you for listening, and Azadeh and you for inviting me, and most of all for the great work that you are doing with betterSoil to help overcome this crisis.
Yeah, very good. Thank you very much, Stefan. It's been good time over the last 1.5 hours. I really enjoyed putting new information in my brain and learning from you. So we stay in contact. And if you want, I don't know if people have questions, maybe they can approach you on Twitter, ask you their questions, or maybe, I don't know, get in touch with you because people want to make network. Would be also interesting for them. And the next webinar, expert webinar, is with Ernst Ulrich von Weizsäcker on the 4th of October at the same time, 4 p.m. And you are almost invited. Stefan, I know that you have received my invitation email. Would be happy to see you there. And that's it, people. My beloved, see you next time in our expert webinar series.
Thank you. Bye-bye.
Goodbye, Stefan.
Bye, Stefan.